So let's thank John again and move on to our second talk by Yuan Su. John, would you mind stop sharing your slides there? Oh, great. And Yuan will talk about a theory of Trotter error. He's from the University of Maryland.
Okay, thanks very much. So I would like to say something about quantum simulation, and the title of this talk is Theory of Trotter Error. And this is joint work, which is done in collaboration with Andrew Childs from Maryland, Ming Chuan from Maryland, Nathan Webb from Washington, and Shuchen Zhu from Georgetown. Okay, so the problem is as follows. You have a Hamiltonian, it's a Hermitian matrix. You have some evolution time, let's say time t. And basically the goal is you try to perform this e to the minus ith up to some accuracy epsilon. So, this problem seems to be very straightforward. Basically, you just want to exponentiate a matrix, but it turns out that is quite difficult for a classical computer. But, on the other hand, the solution of this quantum simulation problem could potentially be applied to many areas, such as in material science or for understanding chemical reactions. Well, it can also be used to design some quantum algorithms, such as digitalizing adiabatic evolutions or designing other algorithms, such as algorithms for solving linear equations. So in fact, this quantum simulation is actually one of the original motivations for Feynman to propose this idea of a quantum computer. And nowadays, especially in this workshop, people talk about near-term applications. And quantum simulation is also one of the potential applications for near-term quantum device. So there are many algorithms that you can use to simulate Hamiltonians on a quantum computer. But perhaps the simplest approach is this approach based on product formulas. So depending on who you are talking with, you could get different names, but they are talking about the same method. So for example, there are some people working on physics, usually called a Trotterization. So they say they have an evolution and then they want to Trotterize this evolution. While other people, especially people working in mathematics, sometimes call it a splitting method. Well, in this talk, I will just call it product formula. In any case, the assumption here is that you have a target system given as a linear combination of terms. And you assume that each term is a Hermitian operator and can be exponentiated with constant cost. So we have already seen this setting in some of the previous talks. In any case, what we can do here is, instead of directly exponentiating this Hamiltonian, what you can do is you individually exponentiate each term like this, and then you put them together. This is sometimes called a first order Lie Trotter formula. It's a first order accurate, so the error will be second order t. Okay, so sometimes it's called Trotter error. In general, you can imagine that you can use more complicated formulas to achieve higher order accuracy. For example, you can use this S2K formula to achieve 2K's order accuracy. So your error will be t to the 2K plus 1. Okay, so this is a very simple method. I should mention that beyond this product formula approach, there has been many other algorithms developed in recent years for quantum simulation. So for example, we have this algorithm based on truncating Taylor series. And we have another algorithm called the qubitization algorithm developed by Lo and Chuang. And also, there's some algorithm based on quantum walk and many other quantum algorithms. You see from this picture that product formula doesn't look very happy because, this more recent algorithm, rigorous analysis shows that this algorithm have improved asymptotic performance as a function of the evolution time and the accuracy. So I guess some people may want to say, let's just forget about product formulas because we have this more advanced, fancier quantum simulation algorithms to use. But this is maybe not the right thing to do because if you actually look at the empirical performance, actually in many cases, product formulas can become the best one to use. So here I have a picture which compares the gate complexity of this quantum simulation algorithms. So you see from this picture that if we only believe rigorous error analysis, then indeed this product formula doesn't seem to perform really well. It has a very large gate complexity. But if you actually throw in all the empirical estimation into this picture, you find that actually product formula becomes the best one. So it has at least a gate count. Well, there's a significant gap between what we can prove for the product formula and what's their actual performance. So, this is something that we need to further understand what is going on here. Well, beyond this reason, there have been many other reasons why we need to continue to study product formulas, although it has been de-emphasized in recent studies from the theoretical side. So, this algorithm doesn't use any ancilla qubits to do that decomposition. It's very simple. So maybe it's more suitable for a near-term demonstration experiments. But on the other hand, this method could be very efficient, especially when many terms of the Hamiltonian commute or nearly commute. Well, in addition, there are some also other good features. For example, if your Hamiltonian satisfies certain kind of properties, such as locality property, for example, you have a nearest neighbor interactive system, then correspondingly your quantum circuits of product formulas will also have some kind of locality property. And this feature can sometimes help you further speed up the simulation if your goal is to approximate local observables. There are also some other applications, for example, in quantum Monte Carlo simulation and also in areas beyond quantum computing. So there are many aspects of product formulas that we can explore, but in this presentation, I would like to focus on only one of them, namely how product formulas can use the commutativity of the Hamiltonians to speed up simulation. So here's our main results. We proved the following, called a Trotter error with commutator scale. So let's say we have a 2K order product formula, this S2K, and we try to simulate this evolution under this Hamiltonian given as a linear combination of terms. Then I claim that the error of product formula will depend on this quantity called alpha computer. So what is alpha computer? Well, it's defined as a linear combination of all the nested commutators of the Hamiltonian terms. So this is an argument about the error of product formulas. It's called a Trotter error, but there's a direct translation that can help you make an argument about the gate complexity. So I won't show you the details, but it turns out that the gate count will also depend on this alpha computer. So this is an important quantity. Well, obviously this quantity is symmetric with respect to the terms of the Hamiltonian. So if you only care about the asymptotic gate complexity, then it turns out that you don't need to worry about the ordering of the Hamiltonian terms. But of course, the constant prefactor will depend on the ordering. There's also a related bound for imaginary time evolution, but I want to talk about that in this presentation. So I guess I won't have time to go into the details of the proof of the theorem, but instead I would like to show you some concrete examples where we apply this analysis, and hopefully this will give you some intuitions. So my first example is a simulation of nearest neighbor lattice system. I guess in the simplest case, you have a 1D system, and you have each term acting on neighboring vertices. And this systems models many important physical systems in condensed matter physics, nuclear physics, and quantum field theory. So there was a previous claim made by Jordan, Lee, and Presque in the context of quantum field theory simulation. So they say, actually product formulas can simulate this kind of lattice Hamiltonians with a complexity that is very close to n times t. So n is the size of the system and t is the evolution time. But they didn't give rigorous justification. So what we can do is we can use our new results to rigorously prove this Jordan, Lee, and Presque claim. So combining with the previous lower bound, we are able to give a very simple lattice simulation using product formulas with nearly optimal gate complexity. Okay, so my second example is a simulation of electronic structure Hamiltonian. So in this case, you have a Hamiltonian, which is given as a sum of a kinetic term and also potential terms. Well, efficient solution of this problem could potentially be applied to understanding materials and designing catalysts. So the best previous algorithm to simulate this Hamiltonian is an algorithm called the interaction picture algorithm, developed by Low and Webb. So this algorithm is, asymptotically speaking, very fast. It's very efficient. But unfortunately, nobody actually knows the practical performance of this algorithm because it's a very complicated algorithm. So what we can show using our new result is that actually you can use product formulas to simulate this electronic structure Hamiltonian with a complexity that is very close to the interaction picture algorithm. So in the special case of second order formula, this actually confirms a recent observation by numerical simulation. Okay, so my third example is a simulation of general K-local Hamiltonian. So in this case, you have a Hamiltonian given as a linear combination of several terms, and each term acts on K qubits, so K is constant. This appears in many areas of physics. So the best previous algorithm to simulate this K-local Hamiltonian is an algorithm called qubitization algorithm developed by Low and Chuang. So that algorithm depends on this quantity called the one norm of the Hamiltonian. So what we can show using our new results is that product formulas can simulate this kind of K-local Hamiltonians that depends on this quantity, this 3 vertical line norm. So we call it the induced one norm. So it turns out that this induced one norm is always smaller than the one norm, and this gap can be significant for many systems. So we get a faster quantum simulation by using product formulas. Okay, so my fourth example is a simulation of rapidly decaying power law interactions. You have a Hamiltonian given as a sum of several terms, and then the size of those terms will decay according to some power law. So the best previous algorithm for simulating such kind of power law Hamiltonians is an algorithm inspired by Lieb-Robinson bounds. So there's some locality that you can use. Well, what we can show is that you can actually use product formula to do something better. So you can get improve the product formulas simulation algorithm faster than this Lieb-Robinson based approach. Okay, next example, clustered Hamiltonian. In this case, you have a Hamiltonian acting on n qubits, and those qubits will group into different parties. You have strong interactions within each party, and you have weak interactions between different parties. So there's a previous algorithm, reasoning algorithm, developed by Peng, Hara, Alzos, and Wu. So they give a hybrid classical quantum simulator for simulating such kind of clustered Hamiltonians. And their algorithm uses product formulas as a subroutine. So we can again apply our new analysis of product formulas to improve the performance of their simulator. Okay, so my final example is a simulation of transverse field Ising model and quantum ferromagnets. So in this case, this is actually not quantum simulation anymore, but it's actually a quantum Monte Carlo simulation. So the goal is you try to approximate the partition function up to the multiplicative error. And so there's a previous algorithm by Bravin and Gossets for simulating these two models. And their algorithm also uses product formulas as a subroutine, and we're able to apply our improved results to improve the performance of their algorithm. Okay, so we have been talking about simulating the evolution operator. Well, in the special case where we only care about the local observable instead of the full dynamics, then we can further speed up the quantum simulation. So specifically, we can show that if you only simulate local observables, then you can simulate that with a complexity that is independent of the system size for power law interactions. As I said, applications, this will imply a Lieb-Robinson bound for power law interactions. Okay, so we have been talking about the asymptotic scaling of product formulas. You ask what happens for the constant prefactor. Well, we redo the numerical simulation of this one-dimensional Heisenberg model that we have saw earlier. So we numerically implement our new analysis, and indeed, this new analysis improves significantly over the previous analysis. And compared with the empirical one, it only loses by a factor of 5. also appears to be tight in practice. Okay, so summary. In this work, we developed some mathematical tools for analyzing product formulas and identify its applications to simulating quantum systems. So specifically to the simulation of nearest neighbor lattice system, justifying the previous Jordanian Prescott claim, to the simulation of electronic structure Hamiltonians, nearly matching the interaction picture algorithm, to the simulation of general K-local Hamiltonians, outperforming the qubitization algorithm, to the simulation of rapid decaying parallel interactions, faster than the Lieb-Robinson-based approach. We have some improved results for simulating clustered Hamiltonians, quantum Monte Carlo simulations, and also some new results for simulating local observables. So underlying all these improvements is a theory that we developed concerning the types, order conditions, and representations of Trotter. So unfortunately, I won't be able to present all the details of the theory in this presentation, but hopefully you have time to check out this paper and discover your own applications. So here's a list of potential problems for future work. I won't have time to go through all of them. And again, you can check it out later if you're interested. And with that, we have a happy ending of this story, and thanks for listening.
Thank you so much, Yuan. That was really interesting. Joanne Camps has a question in Slack. He says, in your chemistry example, is the interaction picture method based on the usual interaction picture of quantum mechanics, in which you absorb free evolution, so you only need to evolve according to interactions? Or is there something else? Does that explain the scaling?
Sure. So that's a good question. So if you look at this Hamiltonian, there's this kinetic term, and then there are these potential terms. So these potential terms in this second quantized plane wave basis, these are number operators. So basically they are diagonalized. So you can directly exponentiate these operators. But on the other hand, these operators are not very easy to implement. So the idea of the interaction picture algorithm is you try to directly exponentiate this part. So this part is very easy to exponentiate, but this part is not that easy to exponentiate. So you switch to the interaction picture and you invoke something called the Dyson series algorithm to simulate the time-dependent Hamiltonian in this interaction picture.
Great, thank you. Jacinta May asks, why did you choose that particular operator decomposition, and could you choose a different decomposition, maybe to maximize commutativity?
Which decomposition?
I am not sure which one she
means.
Yeah,
that would be a great question. So for example, in this theorem, I assume that there's already a decomposition given for us. So we always have this H decomposed as this sum of operators. But indeed, if you have a better decomposition, for example, if you have a decomposition that maximizes the commutativity of the Hamiltonian, then you can get better performance. So for example, in the nearest neighbor lattice system, you always try to group the terms into even odd patterns. So you have these red boxes and blue boxes. And intuitively, this will maximize the commutativity.
She says exactly that's the one she meant.
Okay.
Peter Morgan asks, incredible work, first comment. Thanks. And then for the quantum Monte Carlo examples, I observed some huge exponentials like n to the 19, etc. Is there any physical intuition behind this?
I see. So I'm not really an expert in quantum Monte Carlo simulation, but what we have done is, so this previous algorithm by Bravi and Gosset, they use product formula as a subroutine, but that's actually not the final complexity. So they have to somehow use this subroutine in their quantum Monte Carlo method. So we're only able to improve the product formula part of that algorithm, but there are some other part of the algorithm that we are not able to improve right now.
Great. And another question by Adrien Suau, I'm hoping I'm pronouncing this correctly. How easy is it to compute this new bound for Hamiltonians? Does it require a lot of classical computation?
Yeah, that's a good question. So here I have a picture where we compare the bounds for the 1D Heisenberg model with terms ordered in the even odd pattern. So we have also computed our bounds for the power law interactions in our paper, but we haven't explored the computation for other systems. In general, if the terms in the Hamiltonian, number of terms in the Hamiltonian is very large, then I expect that computation could be difficult to do, but I hope there will be future work that addresses the issue.
Thank you so much for this really great talk. And Yuan also just graduated, he told us, so congratulations.
Thanks, yeah.
And thanks everyone for listening in on this session. The next session will start at 4 p.m. London time, so in 20 minutes. And that will be the second to last session of this conference. So yeah, looking forward to seeing you all there.